This is part 2 of 5.2, and again 5.2 was about Rolle's theorem and the mean value theorem. This part of this movie is going to be covering the mean value theorem. And objectives, I don't have those like I normally do. The objective is to know the mean value theorem and what it states. Just like the previous movie was to know Rolle's theorem. The mean value theorem is actually an extension onto Rolle's theorem, and I just wanted to illustrate that. Here we have the most basic parent function quadratic, just x squared, and what I've done is I've marked off the interval or the points at the endpoints -2 to 2. So here we have from -2 to 2 window, and I marked those x and y values, those points in pink, to match that interval that we're looking at. So what Rolle's theorem stated was basically this: if those endpoints are equal to each other, so something like this situation, then we can assume that between, as long as the function is continuous, we can assume that somewhere in between that interval from -2 to 2 is going to be a derivative or a slope of a tangent that is also equal to 0. So what I do want you to observe is that this secant line that we have drawn between those endpoints are, that being that there is no rise or run because the y's were equal to each other, that slope is equal to 0. So the secant is equal to 0. And what we were also saying is that somewhere in between the tangent line would be equal to 0. So we would have a relative extrema. And in this case, it's a minimum. So there we have that. Let's say that we looked at the interval from -2 to 1. So I have also marked in blue those endpoints on our function. So if you plugged in -2 of our function, again, we would get 4. If you plugged in 1 to our function, we would get 1. Now, those aren't equal to each other. However, we could still draw ourselves a secant line connecting those 2 points. So we could easily calculate that slope of those 2 points by our good old-fashioned slope formula, y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. And what the mean value theorem is going to state now is that we will be able to find somewhere in between these 2 points an equivalent slope of a tangent line. So somewhere right about there is what we're looking at. The idea is this: it's very much along those same lines. Instead of looking for something that's equal to 0, we're going to be actually having to calculate that slope of the average rate of change, so that secant line, and then we're going to have to find the derivative and set the derivative equal to that average rate that we found. And then this is, as long as it's a continuous line, we are going to be able to find that value. So exactly what the mean value theorem states is if f is continuous on a closed interval from a to b and differentiable, so it has to be not only continuous but differentiable, then there exists a number somewhere in between there such that our derivative, so at some sort of x value, our derivative, when plugged in, is going to be equal to that secant line, just like we illustrated. So if you need to pop back up to that visual earlier in this video, please do that. But again, we're now going to, instead of trying to find where our derivative is equal to 0, so instead of setting our function or our derivative function equal to 0, we're going to be setting our derivative function equal to this thing and solving for our c or our x value. So number 3 is going to be giving us this function right here, and they're asking us, can the mean value theorem be applied? And then if so, find all of those values in that interval such that our derivative is, or the slope of the tangent line, is going to be equal to the slope of the secant line of those interval endpoints. So the first thing is we're going to have to look at a couple things of what the mean value theorem states. We're going to have to look at, does it meet the criteria of being continuous and being differentiable over that interval? So first of all, this is going to be continuous because we're looking at just a polynomial, so we know it's continuous. Continuous meant that there were no breaks or gaps. And then differentiable, again, what differentiable means is that basically there are no sharp points, because at those sharp points that indicates a point in the graph that if you approach it from the left and the right, the derivative changed. The left and right derivative approaching any given point has to be the same. And those sharp points, that does not work, so we avoid those sharp points for differentiability. The other thing that we have to watch out for are rational functions with asymptotes, because at those asymptotes the derivative is undefined and therefore it's not differentiable there. So looking at this function, yes, we have a polynomial, it is continuous, and it's not rational, so we don't have to worry about asymptotes or any of those sharp points. I'm going to go ahead and graph this. There it is, our basic x squared. And this is just like the visual that I showed you. We're going to close off the interval the same place as 2 at -2 and 1. So what we're going to have to be finding is what is the slope of that secant line. And the slope of that secant line, here is our a comma b. So what we do have to figure out is this is not a point. We actually have to figure out what are the corresponding y values with these x values of this interval. So to do that, I am going to just calculate my f of a, so f of -2. That's going to be, if we want to, we can even write that. F of -2 is just going to be -2 squared, so we are going to get 4. And then f of b is going to be f of 1, our right endpoint, and that's just going to be 1. So this point right here is -2 comma 4, and this point right here is 1 comma 1. Alright, so we're going to go ahead and calculate then what is the slope of our secant using our just good old formula for slope, our y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. So I'm going to be taking 1, I'll even write that, f of b minus f of a over b minus a, and this is the slope of the secant, or the average rate of change. Alright, so now we're going to be trying to find out where in our function, since we did know that this is continuous, we do know that this mean value theorem applies, and so there's guaranteed some x value that when plugged into the derivative, it's going to be equal to that secant slope as well. So we're going to have to find what is f prime of x, or what is the derivative, and that's just going to be a simple power rule. We're going to be getting 2x. Before, again, when we were using Rolle's theorem, we would set the derivative equal to 0, and then we would find that location, or find that x value for which our derivative was equal to 0. Now we're interested in when the slope of the tangent line is equal to -1 instead of 0. So simply we're going to solve for that x, and it's going to be at x equals -1/2. And I hope that you can kind of see that that's very clear, right? At x equals -1/2 is where we could plug in to our derivative and get that very precise slope. This one's going to be a little bit more involved. We're going to have to graph. We're going to have to find the secant line. So not the slope of the secant line. That's going to involve y equals mx plus b. And we're also going to have to find any tangent lines within the given interval that are going to be parallel or of the same slope of that secant line. So keep in mind it does say lines because there could be several. We don't really know. And so we've graphed. Now we're going to have to find the secant line. I would like to bring up that we would not be able to apply the mean value theorem to this if we had something other than this interval, because we do have something that's undefined here. So if they had chosen a different interval with that undefined in there, we would be able to rule out being able to use the mean value theorem. However, they do close off this interval right there, and what they do ask us to do is then find the secant line of those endpoints. So I couldn't draw the line perfectly, but we're looking for that line right there. What is the equation for that blue line that I have just sketched in? So in order to do that, we're first going to have to find, well, the m part of the y equals mx plus b. So to do that, we just use slope because we have 2 points. So I'm going to begin by finding that point right there, and this is going to be my a, this is going to be my b. So what is f of a if I plug in the -1/2? So I'm going to do that calculation kind of quickly right now. Okay, so f of a is equal to -1 and f of b. Alright, so now to find that slope, so slope of the secant, I am going to be doing that f of b minus f of a, or y sub 2 minus y sub 1, all over the differences of the x's. So here I go with that. Alright, so I just found that the slope of this line is m equals 2/3. So at this point what I'm going to say is I'm going to use one of these. I want the line that goes through either this point or this point, and it has a slope of 2/3. So I am going to now use the fact that I have a given point. I'm just going to use this one right here, which we already calculated was negative 1/2, comma, and then negative 1. So I'm going to use that point and I'm going to plug it in to this equation to solve for my b. So here I go with that. Alright, so I'm going to write up here because I have fear that I am going to be running out of room. We have y equals 2/3 x minus 2/3. That is the equation of that blue secant line that I have drawn. So now, because we do fulfill that this is differentiable over this whole entire interval, and it is also continuous over this interval, I have guaranteed a tangent line somewhere in here that's going to have the same slope of this secant line that we have just come up with. So I'm going to actually draw that in right now. It's kind of hard to see. I should have drawn a bigger graph, but I'm going to have to find that line now. So the biggest thing that I can do for myself is, first of all, find the x value such that the slope of the tangent line is equal to that slope of the secant line. So in other words, I am going to have to take this function and derive it. So I'm going to do that in this space right down here. F prime of x is equal to, and I am going to have to do the quotient rule on this quotient that I have here. So here I go with that. Alright, so here is the derivative of my function, and what I want to find out is when does this derivative, or when does the slope of my tangent line, for what value of x does the slope of my tangent line equal, and what did we say? 2/3. So I want to figure out this right here. I'm going to set this equal to 2/3, and I'm going to have to solve for my x. So the first thing that I'm going to do is I'm going to get this x plus 1 squared off the bottom. So I'm going to multiply both sides by x plus 1 squared. That's gone, which means I'm going to have to do it over here. X plus 1 squared. So yay for quadratics. I am going to divide this side by 3/2. So, I'm going to multiply this side by 3/2. So multiply this side by 3/2. So we have 3/2. Those cancel out. I have x plus 1. Yay for perfect squares though. I'm going to take the square root. We are going to be getting plus minus the square root of 3/2, and then equals x plus 1, and then subtract 1 from both sides. What we are going to be getting is x equals plus minus the square root of 3/2, and I'm going to put a negative 1 out front. Okay, oops, sorry. So we have two locations where we could have the derivative. And what you are going to want though is for it to fall within this interval right here. You're going to be choosing between negative 1 plus the square root of 3/2 or negative 1 minus the square root of 3/2. And what we will want to choose is this one right here. This is the one that actually falls within the interval that we're looking for, and so I'm just going to cross that out. So you can go ahead and simplify this if you would like as a decimal, but what you're going to then do is, again, you're actually trying to figure out what is this equation right here. So what you have just found is the x value that is going to be giving us that slope. So what do you do with this? I'm going to leave you hanging actually at this point because first of all I've run out of room, but second of all is we cannot lose sight of what we have been finding in all this. So I'm going to ask you to finish off this problem and keep in mind what is this value that we have just found, and then how are you going to use that to finish up and find that tangent line. Alright, so the numbers are a little bit messy here, but don't worry, it's gonna be fine. We just have some ugly numbers to deal with. So good luck!